Third speaker in the group of young presenters today is Amek Akarsu from Bristol.
Yeah.
We will talk about short, incomplete Gauss sums and rational points on metaplectic horocycles.
Okay, hello everyone. Thank you for the opportunity to speak here. And today I'm going to talk about short, incomplete Gauss sums and rational points on metaplectic horocycles. So I'm a PhD student at the University of Bristol. Okay, let's start with the definition of the classical Gauss sum. So the classical Gauss sum is defined by G1 of P and Q, and then these are just sum of H mod Q, E, Q, P, H squared. So P, Q are always co-prime integers, and P is less than Q, and EQ of X defined by e to the 2 pi X divided by Q. And then the Gauss sum can be explicitly evaluated by this in terms of G0 mod 4, 1 mod 2, 2 mod 4, and then we have different formula, I can say. So in this case, size of G1 of PQ could be 0, square root of Q, or square root of 2Q. So where A over B is just generalized quadratic residue symbol, and for the Jacobi symbol, we have B odd. And the symbol epsilon A is defined by A1 mod 4, A is 1 mod 4, we have 1, and A is 3 mod 4, we have I. For the incomplete Gauss sum, we have this formula. So now we are interested in the asymptotic distribution of this formula here. So now we are summing over H in integers and f of H over n. This f here is just a periodic Riemann integrable function, could be periodic, and EQ of pH square, and EQ of pH square is just I defined before, and then Q is in Z integers, and then P is in Z Q star, which is the multiplicative group of integers mod Q, and then this set is defined by P is less than Q, and GCD of PQ is just 1. And so we can have an example of this incomplete Gauss sum when f is characteristic function of the unit interval between 0 to 1, and then we get classical Gauss sum G1 of PQ, which I defined just a slide earlier. And then we have in the literature we have Lehmer studied this incomplete Gauss sum in 1976, Fiedler, Urquhart, and Körner 1977, and Oskolko in 1991, and then we can say Paris and others for the recently 19th. So our aim on this study is just study to value distribution of the function for random p. Then we can just choose random p, which depends on ZQ star. So this work is just complements earlier work on the theta sum. So we define theta sum S of x n to be the sum over h1 to the n e of s x h square, for x is between again 0 to 1, and then the absolute value of this theta sum of S of x n distribution of this function studied by Urquhart and Van Horn 81, 82, and 83, and my supervisor Markov give a full distribution of the this function in the complex pair, and you can also see this recent work for Celerasi in 2010 for the general cases of this limiting distribution of this function. So in recent year, in last year, we had a contribution on this subject. So we studied the case when n is approximately q. So this is our theorem with myself and with my supervisor Jens Markov, and which is now accepted and is going to be appear in this year in 2013 in Mathematica. So this is the theorem. So this theorem says that the value distribution of value distribution of this function here, just convergence to this function, or this, I will define this GF plus and GF and GF minus in the next slides. So if you fix a subset D in the unit circle with the boundary of measure 0, and then we choose F to be smooth function, and then for each Q in Z, again we choose P in this set defined here, and then with uniform probability, when Q goes to infinity, we have 6 different cases, 2 here and then another 2, 5, and 6. So depends on Q is 0 mod 4, 1 mod 2, and Q mod 4. And when Q is not a square, Q is a square, Q over 2 is not a square, or Q over 2 is a square case. So the symbol D just denotes convergence in distribution. This one is just a probabilistic definition of convergence in distribution. So which means that the expectation value of this joint distribution of the classical case and incomplete Gauss sum just convergence is x, x, y, and z here, and then the periodic function of this big GFs over here. So expectation value in this case, we have the sum over this function, and the expectation value of these cases, we have integration of this function here. So we can extend this result for the Riemann integrable cases because this theorem only says for smooth case, but we can extend this result to the Riemann integrable function here, as long as with the condition that Q has a bounded number of divisor. So limiting distribution on the theorem. So the random variable here, x takes the 4 values plus or minus 1 plus or minus I with equal probability, and the random variable y takes the values plus or minus 1 with equal probability, and the random variable z takes the values plus or 1 plus or minus I with equal probability, and then all g's here defined by the random variable, and then f hats are just the Fourier coefficients of these functions. And again, x is uniformly distributed on T in unit circle. So to illustrate this theorem, we have some numerics. This is for the case when Q is 0 mod 4, when 5012, we pick Q to be 5012, and then we choose P uniformly distributed in ZQ star. And these histograms shows that the value distribution of this one is the real part, and that one is the imaginary part of this function here. And we have phi of Q, which is the Euler-Tauschen function, and then the Euler-Tauschen function is just 2, 1, 3, 6 in this case. And the red curves here just represent the numerical approximation to the real and the imaginary part of the probability density of this function for GF plus of x. So in the next numerics, we have this time for Q is 5013, and which is Q is 1 mod 2 this time, odd case. So this is the histogram, again with the same function, characteristic function as before, and then phi of Q is this time just 3336, and yeah, you can see the consistency between the histograms and the curve, they all match each other. So the third one for the case when Q is 5014, which corresponds to the case when Q is 2 mod 4, and then this is the function. So the histogram in the right and left shows that the value distribution of the real and imaginary part of this function here, and then this time is phi of Q is 23676, and then the curve again represent the numerical approximation for the value distribution of this GF of GF minus of x. So now we are I am looking for the case when n is between q to the 3, 4 and q, so which is very, very less than n, and very, very big than q to the 3 over 4. So which is short case, then we call this case for the short incomplete Gauss sum. So this is the theorem, and then we have this time 3 different cases, but the condition that we have q is a times q prime, and then q prime is just a prime number, and then we have when q is 0 mod 4, we have this, and for 1 mod 2 we have this, and 2 mod 4 we have this. So this time our limiting distribution are theta series theta sums. Then I will explain this in the next slide. So D again just denotes the convergence in distribution. Yeah. So so we can consider this S of xn as a theta sum with the cutoff function f. So this is just a function on the upper half plane. So upper half plane is just the complex plane with the imaginary part of these points are just bigger than 0. So Markov showed that these are the function on the upper half plane, and then theta f z phi is equivalent to theta f z. So in our theorem, theta f of g is with g is z phi uniformly distributed on this modular surface SL2Z over SL2R with respect to measure this measure over here, dx dy d phi divided by y squared. So this is the limiting distribution, and then random variables x and y is just are the same as before, which is plus or minus 1 plus or minus I with equal probability, and plus or minus 1 with equal probability as before. So we have another numerics for this theorem. So this time maybe you just realize that we have long-tailed distribution in the second case, but in the first pictures, in the first pictures we have like the limiting distribution has compact support here. You can easily see that. But this time our limiting distribution has long-tailed, heavy-tailed distribution. It goes long here and here as well here. So now histograms again represent the real part and the imaginary part. Then value distribution of this function, and the f is a characteristic function of the interval, and then we can pick n to be square root of q, integer part of the square root of q, and q is just 5012, which is just 0 mod 4, but it doesn't matter, you can choose any q. I just pick this one. Yeah. Again, this continuous curves represent numerical approximation to the probability destiny, this time for the SF of xn with x uniform distributed in again unit interval. So I will just define some basic hyperbolic geometry and the group actions on the upper half plane. So maybe you may know this SL2R. This is just a set of metrics ABCD, all the entries from R, and with determinant AD minus BC is 1. So the action on this action of this SL2R on the upper half plane defined by this formula GZ AZ plus B divided by CZ plus D. So G is just the element in SL2R, and then we have a subgroup of SL2R which is modular group. We call modular group. So SL2Z. Now this time we have ABCD in Z, not in integers, and then with the same determinant AD minus BC is just 1. So this modular group just generated by the elements of these two matrices 1 1 0 1 0 minus 1 1 0. So now we can define a horocycle on the modular surface on the coefficient split SL2Z over SL2R here. So the horocycle flow on the unit tangent bundle, this unit tangent bundle defined by the right translation. So we are picking a G in SL2R, and then this just corresponds to G times this special matrix here 1 T01. So these are two different examples for the horocycles. The first one for you can see these are just the circles with the limit point at the real axis here, and these are just straight lines and the limit point at the infinity respectively. So in our theorem 1, the key step in the proof is distribution of ration points on horocycles. So for the sake of simplicity, I'm just going to talk about the distribution of ration points on the horocycle on the modular surface, not the metaplectic group. I assume it's very difficult for technical reason to explain it here. maybe you can ask afterwards if you have any question for the metaplectic group. I can explain it to you later on. But this is the theorem for the distribution of radiation points on horocycles on the modular surface. So now our function, again, smooth function defined here, and then we have PQ in integers, in natural numbers, and then if Q squared y goes to infinity, we have this result, this distribution here. So again, our d mu here, so just canonical Riemann measure, maybe you can call it Haar measure as well, dx, dy, d phi divided by y squared. So this is our measure here. So we can extend this result of theorem to the, as I said, on the metaplectic horocycle. So the proof of this theorem just follows Sarnak's equidistribution, Sarnak's paper in 1981. It's a very famous paper. In the paper, he proved that the equidistribution of horocycles in the modular surface, and then he used Eisenstein series of the even integral case. But in our theorem for the metaplectic case, we use equidistribution theorem from Markov, which used Einstein series of half integral weights. So this is the difference between these two theorems. So the proof of theorem 1. So proof of theorem 1 just follows this equidistribution theorem, radiation points on horocycle, distribution of these radiation points on horocycles. So the first step I just talk about when Q is 0 mod 4, because the other cases are very similar, just are analogs. So we are taking a bounded continuous function, if again complex number to complex number, and then we should show that this one is holds. So this xd is just a characteristic function here. This is just a characteristic function, and then from here to there, you can just use the relation between the Gaussian sum and the relation with this theta sum on the upper half plane and their distribution on that. So you can use this relation from here to there, and then you use test function, this test function, and then if you combine these three of them, you just get easily to the theorem of the proof of theorem 1. For Riemann integrable weights, we will use mean square estimates. So this is the mean square we defined for the short incomplete Gauss sum. This is the formula. And then lemma 1 and lemma 2 says the first one just mean square estimates for the this short incomplete Gauss sum. This is the estimate we get, and then we have Chebyshev's inequality here. So if you combine these two, then you can extend the function, smooth function, to the Riemann integrable function for the proof of the whole thing. So the whole theorem just holds after using this thing over here. I think I will stop here. Okay, thank you for your attention.
There are some questions.
So on the pictures of the distributions, the imaginary part seemed to fit the curve a lot better than the real part.
This one or before that?
I think they all did. So do you have...
Maybe you can just play around with the numbers, maybe you can get exactly, this is just a distribution, so you can't just get the exact, just match. Maybe you just play around with the numbers, maybe you can get much better, like, matching.
So there's no particular reason why.
Other questions? This area is very new to me.
Okay.
So I'm wondering if you can give some background or motivation of why they've considered these Gauss sums with a cutoff function f. Rather than looking at a complete Gauss sum, what's the motivation for introducing this cutoff function f and studying those partial ones?
Oh,
the incomplete ones.
so I define this function here, theta sums, So this work just the distribution of this function given by Markov, and then he showed that the whole distribution of this function and their relation with the horocycles, equidistribution of horocycles. So this is what I use, and then maybe you just realize that if you take x here as like any rational p over q, so you get exactly the classical case of theta sums. So which is exactly the same thing. Yeah, this is the reason I think.
Other questions? Okay, thanks very much.